Hey everybody, it's Mr. Carr again. Today we're going to be talking about 5.3. It has to do with more about polynomial functions, which means we're going to kind of analyze their behavior and what they do. Okay, so for this first example, we'll just talk again about degrees and leading coefficients. So state the degree and leading coefficient of this polynomial. If it's not a polynomial in one variable, explain why. So notice how we're saying in one variable. Okay, quick check on that. Everything is x. So we don't have to worry about the one variable part. We also double check, is it a polynomial? Yes. All of my exponents for the x's are positive integers. So we don't have to worry about fractions in there or negative exponents. So the leading coefficient, the key here is, again, the leading coefficient is going to be the largest degree. So when I look at that, we're looking at the largest exponent with one variable like this. That's this one. So my leading coefficient is going to be a -8. And the degree is going to be a 6th degree. Okay. So again, that is because that is the largest exponent of all the other ones. We got 5 and 2, and then technically x to 0. So that's why it's a 6th degree, and my leading coefficient is -8. And that just kind of confirms that here. It is a polynomial one variable, greatest exponent is 6, so its degree is 6, and leading coefficient is -8. State the degree here and leading coefficient of this one. If it is not a polynomial one variable, explain why. So I'll start with that. It is not a polynomial one variable, but it's still a polynomial. The reason why is because we have two variables here. We got a and b. Okay. So my explanation is we have two variables, a and b, in this polynomial. Okay. Oh, slight delay there. We can still find the degree though. All right. So when we find the degree, we're still going to look at. Oh, okay. I guess we can skip that for this type of problem, the way it's asking. Technically speaking, I can still find the degree here. Always treat this right here as a to the first. The degree of this term is we take our 1 plus 2 is 3. We also have 3 here. So this is still a third degree polynomial. So it's the largest or the largest sum of those. Okay. So I don't know why we're not doing that here, but that's the case. So we have two variables, a and b, so it's not a polynomial in one variable. Okay. But we can still have polynomials in two variables. It's just kind of weird. All right. Volume of air in the lungs during a 5-second respiratory cycle can be modeled by V of t equals negative blah, 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 all of that. Okay. Where V is the volume in liters and t is the time in seconds. This model is an example of a polynomial function. Find the volume of air in the lungs 1.5 seconds into the respiratory cycle. It's talking about a polynomial function. We're just evaluating here. Okay. So that means if it's 1.5 seconds, t equals 1.5. So that's all I'm doing. I'm finding, if I want to find the volume, we're going to say what is V of 1.5. So we'll have negative 0.037 times 1.5 to the third power, 0.152 times 1.5 to the second power, plus 0.173 times 1.5. And that's all we're doing. We're going to go ahead and multiply all these out and combine our values together. Okay, so if I do it step by step, I'll do negative 0.037 times 1.5 to the third power. Okay, make sure if you're doing this like multiple steps, do your exponent first right here, and then do the multiplication, or at least put them in your calculator properly. So I have negative 0.1, and let's go with 3 decimal places, 125. Okay, so then I'll do 0.152 times 1.5 squared. And that's going to give me 0.342. And then 0.173 times the 1.5. And that's going to give me 0.260 when I round that off. Then we'll put these all together. Okay. So I got negative. So here we got that one plus that 0.2 plus 0.2 Okay, put them all together, round it off. We got 0.477. And this was volume in liters, so it'll be liters for my label. Okay, that's it. We're just evaluating our polynomial functions there. So we're just using function notation and make sure we put the put the input in the right spot and then do our correct order of operations. All right, function values of variables here. So find b of 2x minus 1 minus 3bx if b of x looks like this. So this is an interesting one because we're basically saying in this function notation here, we're manipulating the original polynomial function. It might help if you do it this way. We're going to start off by doing b of 2x minus 1 as its own thing. What we're saying here is if this is b of x and I want to know b of 2x minus 1, that means 2x minus 1 is my input that goes into both of those x's. So this is what it looks like. It'll be 2 times 2x minus 1 squared plus, 2x minus 1 minus 1. Okay, so I'm going to go ahead and multiply that out and simplify that. So this is going to be 2 times, we're going to multiply this first to help that, it'll be a little easier that way. So I'm distributing 2x minus 1 times 2x minus 1. Remember, this is the multiplication I'm doing here. So I got 2x times 2x is 4x squared minus 2x from here and a minus 2x here. So it's going to be a minus 4x, then a plus 1. I got plus 2x minus 1 and then minus 1. Okay, we're going to go ahead and distribute this now. So I get 8x squared minus 8x plus 2 plus 2x, and then I'll just put these two together and make it a minus 2 at the end. From there, I'm just combining my like terms. So I've got negative 8x, positive 2x, positive 2, and negative 2. So b of 2x minus 1 is equal to 8x squared. Negative 8 plus 2 is a negative 6x, and then positive 2 and negative 2 actually just cancel each other out, so it's done. All right, so the other thing I want to do is 3bx, 3 times b of x. So I'm going to do that as well. So I got 3 times b of x. Whoops. Yeah, 3b of x. We're basically just saying we're taking the function b of x and just multiplying the whole thing by 3. It's a little bit easier than the previous one. We don't have to do a new input. We're just multiplying the whole function by 3. So 3b of x is equal to, distribute that out, 6x squared plus 3x minus 3. All right, so now if I want to find this, we have these two individually. We're just going to subtract them. Just make sure you're careful when you subtract the 3bx though. So b of 2x minus 1, remember that is going to be 8x squared. Oops. 8x squared minus 6x. Then you're going to subtract the entire 3bx, which is going to be 6x squared plus 3x minus 3. So combine like terms after we distribute this negative sign. So it's going to turn into 8x squared minus 6x squared minus 3x and then plus 3. Remember what I'm doing here is I'm taking this, we're doing it to the opposite of everything inside the parentheses. So x squared and x squared, negative 6x and negative 3x, and then 3 is by itself. So 8 minus 6 is going to give me a positive 2x squared. Negative 6 minus 3 is a negative 9x, and I still have positive 3 at the end. And that's it. That is my final answer. That expression represents this idea right here. That was a lot. So this one, we're going to look at some graphs, a little bit easier, but we just got to make sure we're clear on the terminology. Graphs of our polynomials. Here's some things that we're going to be doing when we look at the graphs of a polynomial. We want to describe the end behavior. End behavior is the direction the graph goes as x goes to a positive and a negative infinity. So what I mean by that is, as it goes to the left, what's happening to the end of this? Well, it's going down. As it goes to the right, what's happening to this end? It's going down as well. Here's how we like to describe this. As x goes to a positive and negative infinity, it looks like this. X goes to infinity, x goes to negative infinity. Okay, the direction of the graph. So we're like, when we talk about end behavior, it's always going to be these two things to start, because we want to say what's happening when it goes off all the way to the right forever and all the way to the left forever. The second half of each of these is you're describing what happens to f of x. Okay, so f of x is going to approach something. This can change. Okay, for this example down here, f of x, yeah, I'll write it here. So I'll say x approaches negative infinity on this side. F of x is also approaching a negative infinity. Okay, you can approach infinities, positive or negative infinity. You can also approach values. Talk more about values in the future. Okay, on the right side, x approaches infinity. F of x approaches negative infinity as well. Okay, so that's my end behavior. Basically, we're filling this in with whatever the graph is approaching as it goes on forever. Okay, determine whether it represents an odd degree or an even degree. Even degree has both arrows going in the same direction, which is what we have here. Okay, since they're both down or both up, that's an even degree. Odd degree is going to have one arrow goes up and one arrow goes down. So it's going to look this way or this way. Okay, so maybe I have like just a straight function like this. That's lower left, upper right. That's an odd function. Okay, or the graph could look something like this. Still an odd function because it's lower left and upper right. They're opposites. The other thing we want to do is state the number of real zeros. And that's just the number of times the graph touches or crosses the x-axis. So in this case here, for this graph, no real zeros. Okay, so I have an even degree and no real zeros here. So that's what we're going to do when we analyze graphs. We want to find the end behavior, the degree, if it's even or odd, and then the number of real zeros. Okay, so that's what we're going to look at for this example. Okay, for this graph, determine the end behavior. So as I stated, so I don't call it A, B, and C. For part A, you're always going to do this. X approaches infinity, X approaches negative infinity. Okay, you'll always have that to start it. So as X approaches infinity, whoops, it's going to the right forever. The graph here is going up forever. So that means f of x also approaches infinity. If I look to the left forever, the graph is going down. So that means as x approaches negative infinity, f of x approaches negative infinity as well. Okay. Part B, determine whether it is odd or even. Because it's doing the opposites, this is going to be an odd degree. And that's it there. State the number of real zeros. It crosses at one time. That's all I care about. It has one real zero. Okay, and that's it. So we're looking at those three summaries. That is everything that we need for describing the graph. Okay, and that is going to be it for 5.3. So we're just starting analyzing a little bit of our polynomial functions. This is going to be a common theme for the rest of the unit. So take care, everybody.